Good afternoon, everyone. As Katie just mentioned, I'm an assistant professor in the School of Civil and Construction Engineering at Oregon State University. I teach virtual design and construction contracts, planning and scheduling, and in my research, I study remote sensing and IT technologies for construction engineering and management applications. And today I'm going to talk about how we can leverage laser scan point clouds and drones to measure concrete floor waviness and flatness automatically. This is an ongoing research, and I will present the preliminary results today. Our learning objectives are to, first we will talk about commonly used procedures for measuring concrete floor flatness and waviness. And we will identify the characteristics of laser scan data as well as two-dimensional continuous wavelet transform that we use to process the data. And we will compare our methodology to the current commonly used current methodologies to measure concrete flatness. So why measuring floor flatness is important? A step back, this is a more common term is used is the dimensional quality assurance and quality control. As we all know, as-built dimensions of cast-in-place concrete often differ from the dimensions originally specified in as-designed plans. Dimensional quality control verifies that elements are constructed in compliance with the specified dimensional tolerances, and failure to detect the imperfection in the newly constructed surfaces during the earlier stages of construction may cause delays when in carrying out necessary repair works, and this can be very costly. Therefore, it's very important to carry out those inspections in a timely manner. So focusing on concrete slabs, there are several factors that affect the dimensional quality of cast-in-place concrete slabs, such as temperatures, placement, and finishing techniques that are applied during construction. And proper regulation and control of these factors are essential for achieving specified levels of waviness and levelness. And the defects resulting from waviness of concrete slabs not only create aesthetic issues but also affect the efficiency of lift trucks and very narrow aisle vehicles. Even if waviness present in slabs is not immediately noticeable, the waviness of the slabs in industrial facilities such as large warehouses must be examined because failing to detect those waviness and deviations from the specified tolerances may affect the operational activities that the floor is designed to handle. Here on the left figure, you see a very narrow aisle vehicle, and as you see, the irregularities on the floor may affect the operation of this vehicle and may cause static lean. The current methodologies used in industry are straight edge, F-number, and Waviness Index methods. Can be very time consuming and tedious, especially when measuring large surfaces such as large warehouses. And these methods entail surveying one-dimensional lines for differences in elevations and characterizing the undulations of specific periods on the surface. For example, straight edge method involves laying 10 feet straight edge across a survey line on the floor and measuring the distance between the straight edge and the floor using a stainless steel slip gauge. The results obtained using these methods are easily comprehensible, but the laying out the straight edge over large surface areas is labor and time intensive, and there may be random errors in measurements. Then the F-numbers method enable measurements of elevation differences at fixed intervals to produce more accurate results. It provides results in the form of two numbers, floor flatness and floor levelness. They do not have any dimensions, so that's one of the drawbacks of this method, that the results are not easy to comprehend, and also it provides the information for only given certain floor undulations. And the Waviness Index method was described or developed after F-number method, and it provides information for floor undulations between 2 feet and 10 feet This is important because it corresponds to the periods of surface undulation that affect the operation of forklifts. So the results obtained using Waviness Index method are expressed in inches. They're relatively easier to understand. So despite having significant advantages over straight edge and F-number method, Waviness Index method shares similar drawbacks with those methods. The measurements are sparse, and they fail to guarantee that the collected data is an accurate representation of the geometric features of the entire surface. And therefore, it's hard to apply these methods to large floor areas such as warehouse projects. And also the other thing is that since there are only the measurements are collected from certain places, it is not easy to provide the location of those undulations as well. Sorry, I went back. Okay, so we wanted to see if we could leverage Lidar and drones for to collect the data and get the waviness information from that floor. For those who are not familiar with Lidar and drones, Lidar is also called laser scanners. They're basically high definition surveying equipments. The data you collect from using a Lidar equipment is basically a three-dimensional point cloud, where each point is associated with XYZ coordinates, and if there is a camera, it is also associated with RGB color information as well. So the use of laser scanners and drones within the last decade in the architectural engineering construction industry has skyrocketed. There are different, you can use these tools, technologies for different applications, such as building damage assessment after natural hazards, landslide inventory. You can use the data to quantify road roughness, progress tracking, and dimensional quality control is one of those. You're perhaps familiar with drones, hobbyists use it, construction contractors started using it. The one thing about drones is that you can also attach different types of sensors to them. So it can be a regular digital camera to collect digital images or videos. You can attach a thermal camera, and you can also, in our case, we attach the Lidar sensor to the drone. So the Lidar sensor that is on the drone here and the Lidar sensor here are different in terms of accuracy. So this Lidar can collect a laser scan that is very, very dense and accurate. So the laser scan, the Lidar data we collect using the drone is fairly less accurate. So essentially you're collecting less points, less data points. I will talk more about that in a little bit. So our objectives were to see whether we can characterize the entire floor using this laser scan data instead of using one-dimensional survey lines. We also wanted to look at the required data quality for the point clouds, because lasers, it may be computationally very difficult to process laser scan data if it's a very large project. So the point, if you can obtain the same results with a lower quality data, that is better, because it's computationally it's easier to process that. So we also wanted to look at that, and we wanted to compare the tripod-based, also called terrestrial laser scanners, versus drone-based point clouds to characterize the surface waviness. Our methodology, when you collect the point cloud data first, the raw point cloud data consists of data points in this case, from a concrete slab, as well as its surrounding environment, including workers, equipment, surrounding buildings. The point cloud is typically, for any project, typically a result of multiple laser scans registered together using a target-based approach. In our case, you will see in a little bit, we registered 3 different laser scans together. And then once we remove the noise, remove the information related to the workers, equipment, that is called pre-processing, and then we developed the depth map, where we used as a signal to our continuous wavelet transformation, and then we were able to detect and localize the undulations that were present on the surface. And then we could look at the compliance with the specifications at the end. I'm not going to get into the mathematical details of wavelet transformation, but wavelet transformation has a wide range of applications in engineering, some of which include seismic signal analysis, sound pattern analysis, and quantum mechanics. Continuous wavelet transform of a given function basically is the inner product of the function with the scaled and shifted versions of the mother wavelet. This implies that the function has to move above and below a certain axis in a wave-like manner. Here, this figure shows a typical wavelet function. Is commonly known as Mexican hat wavelet. So as you can see, this here, this function has similarities with possible undulation on a concrete surface. That's why we chose to use Mexican hat wavelet as our mother wavelet function for this project. And then we apply this continuous wavelet transform. It's like a wave-like properties to define and characterize those undulations on the surface. This is the first case study I wanted to talk about. This was we collected data from a warehouse concrete warehouse project. This is a concrete slab. We used a terrestrial laser scanner. This is a Leica P40. It's one of their recent products. We did the scanning within 10 hours after the concrete was poured. And the whole data collection took us about, with all the setting up and everything, took us about 45 minutes, which is faster than collecting data using the traditional methods for waviness measurements. And this shows the entire laser scan. This is our area of interest here, this red portion. So we removed all the other data points from the point cloud, since we weren't interested in those parts. We use the regular off-the-shelf point cloud processing software to remove those points. The original point cloud you saw in the previous slide had about 100 million points. After we removed the points that we weren't interested. We only had the points that were for the concrete slab, and then we converted that into a depth map that had 1 centimeter in intervals in both horizontal and vertical directions. And for each of those, we calculated the z coordinates at each grid point that were calculated. This figure basically shows the result. So as you see, the height differences with respect to XY plane varies between -2 to 2 centimeters. This is, and you see that these are like the possible likely areas that has some undulations. Because that differs from that average height. And then we applied our the two-dimensional continuous wavelet transform here. So here, these scales, scale 15, again, without getting into mathematical details, scale 15 basically corresponds to 2 feet. So the undulations that are present on the surface in periods of 2 feet and 30 feet. Here you see there's a likely peak here and here as well for scale 30. This corresponds to 4 feet. And this kind of makes sense. There's no everything else is pretty much at the same height, and this makes sense that in the previous depth map we saw that the slab is relatively flat with a few little peaks. In fact, the average value of the deviation in the z-axis in the height was 0 centimeter with a standard deviation of 0.3 centimeter. And the next slide shows for the other 3 scales that we investigated. These correspond to 6, 8, and 10 feet. Here you see the same little peak here. And in addition to that, in scale 60 and 75, you see an additional peak over here. So these show possible undulations in those at those locations on the slab. This figure basically shows we applied 5 distinct periods, and this one shows the periods between 20 centimeters to 400 centimeters that corresponds to 0.65 feet to 13 feet. The advantage of our approach is that we combine the 3-dimensional data from laser scan and 2-dimensional continuous Wavelet transform. This can support the analysis of waviness with essentially any characteristic period, or like in other words, is wavelength. So this enables that the approach to study waviness not just for few distinct wavelengths like 2, 4, 6 feet, but for dense and large ranges of wavelengths. And this is basically, this figure demonstrates that these ellipses shows possible areas of defects for these periods. I'm going to, in the interest of time, I will skip some of these, but we also then we applied the continuous wavelet transform. We looked at we applied the Waviness Index method to our point cloud data, and we compared the results to the length adjusted RMS deviation. We call that as a LAD, to our results that we obtained from the 2-dimensional continuous wavelet transformation. We selected 30 survey lines, 15 along each axis. I'm going to quickly go through these ones. So the results show that the length adjusted RMS deviation, basically the results that we obtained using the Waviness Index and the results we obtained using the continuous Wavelet transform were highly correlated. That basically show that our method has promise in terms of finding those deviations and also locating them. So this table basically compares these methods as I just talked about. You can only get information about the periods of undulations for certain periods. Using our method, you can identify those undulations for any period. You can visually, the output is a depth map, so you can see the actual location. The errors aren't random errors. There is some systematic error that comes from the laser scan instrument itself. The data collection is very fast, and the data is it is not sparse. You can get a dense point cloud and find those undulations for an entire surface. and also it comes with that you can also visualize that data. I will go over this case study quickly. We wanted to compare the drone-based laser scan to terrestrial laser scan shown here. We collected data using both of these, and from the previous study we considered that the results we obtained using the terrestrial laser scanner as the ground truth, and then compared our results accordingly. So this is a Magruder Hall expansion project. It's a building at Oregon State University campus. These are the equipment we used, Leica P40. We collected 2 scans, registered them together in the same coordinate system, and then we collected drone data with a Lidar unit on it. We did 2 passes. The spatial resolution here, I would like to show this, that it was fairly low compared to what we had here. This is 5 centimeters spatial resolution, and for the terrestrial laser scanner was 5 millimeters. So basically you have less points to identify the surface. So again, similarly, we used the off-the-shelf software to clean up our data. We removed the noise, and we developed the depth map. And after we got the depth map, we applied the 2-dimensional continuous Wavelet Transform for the same scales as the previous study, 15, 30, 45, 60, and 75, which corresponds to 2, 4, 6, 8, and 10 feet. And these are the results we obtained. As you see, this is the ALS, the drone-based data, and this is the terrestrial laser scanner data. As you see here, there's an undulation that was detected when we used the actual laser scanner. The terrestrial laser scanner, we could not detect that when we use a drone-based one. Same goes for 30. These are similar. It pretty much captured this, but there's an issue here in this part, and we couldn't detect that in the ALS drone-based data. For scales 45 and 60, they pretty much correlate with a difference. There is a false positive here in the drone-based data, and for scale 60 is it's pretty much the same. It's a little different there, but the other one shows the same, shows some irregularity in that area as well. And for 75, the results correlate with each other. So we looked at the recall precision and accuracy values for frequencies. For scales 60 and 75, they largely agreed in terms of detecting those undulations. But for other scales, they were different. This is, we thought that there are several reasons. The accuracy, the spatial resolution of the drone is lower. And the other thing is that it was our first experience with this. We figured that we should have flown the drone at a lower altitude. So the drones have advantages, right? You can collect data non-intrusively because construction sites are dynamic. You don't want to interrupt the current operation. So if we can use drones for this purpose, that is perfect. And we're currently still working on this. Again, we obtained comparable results for the 2 feet, 4 feet, and 6 feet undulations, and we obtained different results for scales 15 and 45, which corresponds to 2 and 6 feet. Again, one of the things that can be done is flying the drone at a lower altitude, and increasing the number of passes could also help to increase the resolution of the point cloud that you obtain. We have several papers that you can check out. I provided the links here as well. That I think I'm a few minutes early. If there are any questions, thank you.
So the first question is, will these scans using Lidar and drone technology work in the dark, number one, and will puddles of water on the slab affect the readings?
The answer to the first question, yes, because Lidar uses laser scans. They're in the near infrared region of the electromagnetic spectrum. So yes, it does work in the dark, and the water does not affect the results that you obtain.
Okay, our next question is, you used the word, quote, defect, which generally implies unsatisfactory performance. By what standard or specification were the locations noted as defective?
I guess I was I was referring to the deviations from the specified tolerances. So that was my I guess saying by defect, and that's what I meant. So whatever that tolerance for the concrete slab is for a given project.
Okay, great, thank you. The next question is, what type of targets are used with drones as compared to targets using the Leica scanner?
Similar. Again, you can also do point cloud based registration together, but usually regular targets, whatever that can be seen in the, as long as they can be seen in the point cloud, so that in the point cloud processing software, those targets are used to register those points together. So.
Another question following up on the darkness and water concerns, do construction personnel on site have any impact on the results?
Yes and no. When you're using the so if they're in the laser scans, you need to remove that data because it is not relevant to the waviness of the project. Let's say there's a large equipment on the concrete slab that you're trying to scan and characterize the waviness. Obviously, you won't be getting any data points from there, right? So that is going to affect the results. So preferably, you don't want to have large equipment and workers being in the laser point cloud. We remove those during the post-processing, but they don't have a high impact in the results.
Okay, our next question is, did you correlate the high spots with actual places on the floor?
Did I correlate the high spots with the actual places on the floor? Yeah, well, that's what we showed that on the, I'm not sure if I understood the question correctly, but yeah, we were able to get the locations of those spots that were, there were slight undulations on the surface. We were able to get the exact locations of those.
Our next question is, what is the resolution of the vertical data with the drones? It appeared to be approximately 0.1 centimeter on the result plots.
Vertical resolution?
Yes.
I cannot. So I'm not exactly sure. So the spatial resolution, in other words, the spaces between those points were about 5 centimeters. But I'm not exactly sure about the vertical resolution. I would say that is also about 5 centimeters.
We do have a couple more questions, Yelda, if you have a few more minutes, if that's okay.
Sure.
The next one is, does the drone hover, or how quickly is it moving across the slab? Does it maintain a position for a while and then assume a new position?
It hovers. So I didn't actually fly the drone. A colleague of mine did that. So we first identified the path for the drone to fly. It can hover, but we didn't do that. So we had certain lines that we wanted the drone to fly. So and we didn't want it to be too close to the. So we were flying at 60-meter altitude, but it can hover and do those. It can hover, or we could have flown it at a lower altitude as well. But we usually you can pre-program the path of the drone's path.
Okay, and one final question for you, Yelda. Is it possible to determine the density of the concrete through this laser technology?
Density of the concrete. I'm assuming this is like the density of the material. Is that what?
That's what I'm thinking the intention of the question is, yeah.
No, because laser only collects data from the surface. It doesn't go below surface. So just the surface information. So we cannot really tell the density from that using laser scanners.
Great. Well, thank you for your presentation this afternoon and for fielding the attendees' questions.